Welcome to the fourth video on growth models. This is going to be a lesson on linear and exponential growth applications, and we'll look at stamp collecting, we'll look at yeast cell growth as well. So just to review quickly the linear formulas that we will look at. Recursive formula, P sub n is any particular value in the sequence, and it is equal to the previous value. P sub n minus 1 is the previous value plus d, so that's a constant difference. So each term in a sequence increases or decreases if d is negative, increases by the same amount. An explicit formula is any term in the sequence is that constant difference times the n, the number of term that you're looking for, plus p sub 0, which is the original or the starting point. Exponential formulas, as we had the recursive formula, which is any term can be found by multiplying b, which is the constant ratio. B is a constant ratio by the previous term. That's the recursive formula. The explicit formula is just by taking, find a term by taking the initial value, p sub 0, the starting point, and then raising that constant difference to the n power. Now, we're going to approach something a little bit different. We'll talk about this. And notice this formula and this formula are very similar. Instead of a b to the n, this is 1 plus r to the n. Because r, notice it says b here is 1 plus r, because r is like a growth rate or growth factor or a decay rate. So if something's increasing by 20%, for example, r would be greater than 0. It is 0.2, so b would be 1 plus the 20%, or 1 plus 0.2, so b would be 1.2. So sometimes if you're given the rate, a growth rate or a decay rate, which would be negative, for example, if something was decreasing by 5% every month, for example, then you'd have 1 or 100% minus 5%, or plus a negative 5%, which would be 95%. So b, the constant ratio there would be 0.95, because you're going down 5% each month, or whatever period that the growth rate is based on. So let's take a look at this first one. We'll determine whether it's linear or exponential by just reading it and seeing the context. If it's we think it's a constant difference or a constant ratio. So Sam is a stamp collector. She currently has 1,200 stamps. That's our initial amount, apparently. Every month she buys 5 new stamps to keep her collection growing. Now, when you buy 5 new stamps, that means you're adding 5 each month, which is a constant difference. So D is equal to 5. Also note that if we start at the current time, if we talk about P sub 0, the initial value, that would be 1,200. So that's the basic facts you can get from this. We know it's linear then, right? This is linear. And so to write a recursive formula for the number of stamps, recall that the linear formula is any term, P sub n, is equal to the term before it, P sub n minus 1, plus d. Well, all you need to know the recursive formula is that d is equal to 5. So P sub n is kind of like y, is equal to P sub n minus 1, the term before any x value, plus, in this case, 5. That's the recursive formula. It's not very convenient to have a recursive formula. All this really is helpful when you want to compare like one term to the next term. Adjacent terms, they're always 5 apart. But if you had to go all the way to like the 100th term, you would have to know the 99th term and add 5 to it. And then to know the 99th, you'd have to know the 98th. So you'd have to go through the whole sequence on a recursive formula to get up to 100, unless you know what the explicit formula is. And we'd switch over to that. And remember the explicit formula, that is P sub n equals d times n plus P sub 0. Well, they gave us a P sub 0, a starting value of 1,200. So P sub n is equal to 5 times n plus the 1,200. So the explicit formula for a linear model is really convenient. It says find the number of stamps Sam will have 2 years from now. Now, let's go back and recall that it was 5 new stamps every month she was going to buy 5 new stamps. So that 5, that was really 5 stamps per month. So when we use this formula, N has to represent the number of months. And in 2 years, to use the 5, we've got to use that as 24 months. So we convert that. And so after 2 years, that would be the 24th month. So P sub n equals 5 times 24 plus 1200. And you could use your calculator if you wanted. That's 120, and 120 plus 1200 is 1320. So that's the number of stamps after 2 years. Now, even more importantly, when you're using an explicit formula, is when you have to find out how long it'll take to collect 2,000 stamps, for example. So now, note the difference. Here you knew the length of time. We could calculate that n is 24, but here we're finding the answer. Well, that's our p-value. That's 2,000 stamps will be after you've collected for n, the unknown number of months. So that makes sense. If you already have 1,200, then obviously if we subtract 1,200 from both sides, that means really we're asking how long will it take to collect 800 more. When you divide by 5 on both sides, you can use your calculator if you want, but 5 goes into 8 one time with 3 left over, so that's 160. It will take 160 months. Now let's take a look at another situation. Let's say that we're brewing beer, and it requires healthy growing yeast cells. So yeast has to multiply. Yeast is a crucial element in most beer. So during the high growth phase, healthy yeast cells have an hourly growth rate of about 58%. That's what they look for in good yeast, and they do some testing. And if a scientist's they might test to make sure this is good, healthy growing yeast. So let's say a scientist's initial count of yeast cells in a diluted sample is 120. Now you have to delete yeast cells because otherwise, well, you could see from that original picture that, yeast cells this is quite magnified. They get really super dense and you couldn't count them really. That's probably diluted right there actually. So anyway, so how do we do that problem? Now, first we got to determine, does that sound like a linear or an exponential? And if you recall, in the exponential, we have growth rates. Those are exponential when there's a percentage growth rate. So in the previous one, we were increasing the number of stamps by 5 stamps every month, the same amount, 5, and then 5 more, and 5 more, and 5 more. This increases by a percentage. So after, this is an hourly growth rate. After an hour, if it increases by 50%, 58%, you'll have a lot more yeast cells, and then the next hour you'll have even more. 58% of a bigger number will be a larger amount. So that's what exponential growth is about. So we're going to use the exponential growth formula. So let's take a look. Let's assume it's supposed to have a growth rate of 58%. So if we write a recursive formula for the number of yeast cells in the sample, a recursive formula, right, that's going to look like this: P sub n equals B times P sub n minus 1. Now remember, B is 1 plus R, the growth rate. So this is a growth rate of 58%. R equals 0.58. So B is equal to 1 plus 0.58, or 1.58. So we get P sub n is equal to B times P sub n minus 1. So 1.58 times P sub n minus 1. Now, a more comfortable, an effective formula is usually to get an explicit formula. So that is this formula. We've already calculated B. So we'll take P sub n is equal to, now the initial amount, P sub 0, was 120. So we have 120 times 1.58 to the n power. And now we ask, how many yeast cells would you expect after 90 minutes? Well, that is, let's look at this. This growth rate, we might want to note, is an hourly growth rate. So 90 minutes would be equal to 1.5 hours. So remember that n has to agree in units with the growth rate units. And so to calculate this, we're going to say P of 1.5, not P of 90, equals 120 times 1.58 to the 1.5 power. So we'll do that on our calculator. 120 times 1.58 to the power of 1.5. And that is equal to 238.32. Well, since they only gave us a couple significant figures, if you write 238.3235, whatever, you're not really going to have fractions of a bacteria. Let's just give an approximation of, let's say, 240 cells, right? Yeast cells. I think I said bacteria, I meant yeast. So now the next question asks is, when is the number of yeast cells expected to reach 500? So let's take this formula, P sub n is equal to 120 times 1.58 to the n. And now, when it tells us the number of yeast cells, that's what P sub n stands for, right? P sub 1.5 was the number of yeast cells after 1.5 hours. So now we already know that we want 500, and now we ask, when should we expect that? And how do we solve that? Well, we want to isolate n, so we've got a multiplication of 120. We will divide by 120. And so we'll get 50 divided by 12. So I'm just going to do that on the calculator and leave that in there. Now you could just leave it as 50 over 12. It is 4.16 repeating. I guess I'll write that as 4.16 repeating. And then that should be equal to 1.58 to the n power. Now, do you recall how to solve an exponential equation when the unknown is in the exponent? You can take the logarithm of both sides. So one method is to take the log of both sides. Now, some teachers teach that you always take the natural log, so we'll do that on this one. The natural log of 1.58 to the n power. And the general rule is here, if you've got a log of a power, then that exponent can come out and be a multiplier, a factor. And that gives us the natural log of 4.16 repeating. And that is solved for n. All you do is divide by the natural log of 1.58. So fortunately we already have the 4.16 in the calculator. So I'll take the natural log of, now I can go second answer, that's the 4.16 repeating, and I'm going to divide that by the natural log of 1.58. And that gives me 3.119. So I'm going to round that off to about 3.2. Now that is, remember, this 58% was an hourly growth rate, so that's 3.2 hours. And that's what is expected of healthy beer yeast. Now, another way you could do this, you may have learned this method, and this is perfectly fine too, that is when you have an exponential equation, you can rewrite it using a logarithm, and the base of the exponential becomes the base of the logarithm, 1.58. And then the n is our answer. The exponent is always the output of a logarithm. A logarithm gives you an exponent when you take the log of something. So you take the log of 4.16 repeating. Now, this is the formula for the log of something where you've got a base that you're not comfortable with or you can't use directly on your calculator. Log base a of b is equal to the log of b over the log of a. So this becomes the log of 4.16 repeating over the log of 1.58. and you can use the natural log too, ln and ln, as long as you use the same log. That's fine, natural log or common log. But you'll see you'll get the same exact thing. You'll get 3.2 hours that way too. Okay. And that is all for that video. We'll stop there. And you know, there's other videos on logistic growth that are in the video block, and you should watch that. There's also other videos on more exponential growth problems, and that would be valuable as well. Okay, best of luck.